Alright, this is a small lesson, a short lesson on the frictional force. So what we're going to look at today is the concept of friction, what it is, and how we can calculate its effect on an object that is stationary or moving. So the first thing that we want to talk about is the frictional force is F subscript F. That's the symbol that we give for it. It's clearly measured in newtons since it's a force. And it's basically the force that resists the motion of an object. So if an object is stationary and you try and push it, it's the resistive force that you would feel as you try and get that object to start moving. Not the inertial resistance, but the actual the contact resistance between the two objects. So you know that pushing an object that's on rough surface compared to pushing it if it were on really smooth surface like ice or something like that, that clearly there's a difference between the resistive effect of those two surfaces. So how can we determine the magnitude or the strength of this frictional force, this resistance to an object's motion? This isn't like inertia, like when I say resistance to motion, that's a physical concept of matter. We're talking about a force that exists between the contact of two surfaces. So there's really two factors that this plays a role in. And I mentioned the first one, which is the surfaces in contact. So the surfaces in contact are a big part of how we define how much resistance there is by the force of friction. So clearly, if we have a steel blade on ice, that will have one particular amount of resistance or friction that we can talk about. Whereas if we have a steel blade on sandpaper, that's going to have a different type of friction. If you rub your hand across sandpaper, we know it's got quite a bit of friction, whereas if you move it across a smooth desk, you can feel there's less friction. So definitely it's all about the two surfaces that are in contact. So it's the surfaces in contact, and basically it's between two surfaces, and they must be in contact. Now, there's a symbol for the measurement of how sticky two contact surfaces are, or two different types of surfaces are to one another, and that is given by the symbol mu. So this is the symbol mu, and it's called the coefficient of friction. Okay, it's a Greek letter mu, it's called the coefficient of friction. So that tells us how sticky two surfaces are to one another. If that coefficient mu were to drop to 0, meaning there's no coefficient, the coefficient of friction is 0, that would be by definition a frictionless surface. So if you had two objects in contact with each other, there would be no friction between them. Theoretically impossible, but still we can get really close to 0 friction, but we can't get rid of friction entirely. So mu is typically never 0. But in many cases, just to make life easier, especially in physics calculations, we can assume for many instances that mu is equal to 0, just to make it easier for now. Well, what else could be a factor in the amount of frictional force that an object feels? Well, that something else is, in fact, a lot of people will say, well, maybe it depends on how heavy the object is. So, you know, if you have a light object sitting on a surface that's made of the same material, let's say a cardboard box on rug, if you put a lot of objects into one of the cardboard boxes and you change the weight of the object, it would obviously feel more friction. There'd be more resistance force in terms of friction, not just the resistance due to inertia, but there'd be more friction because the two surfaces would be in tighter contact with one another. And that sounds great. However, what if that box was heavy, heavier than a previous box? The two surfaces in contact are still the same. But someone comes up and lifts up slightly on the box. Well, the weight of the box hasn't changed. The weight of the box is still the same. However, I've lifted up just a little bit on that box, so it appears lighter. Well, as soon as I say that the contact force appears to be less than the weight of the object, what I'm really talking about is what? Now, you've probably said, hopefully, we're talking in that case about this, the normal force or the contact force. So it actually matters more about how much contact force there is. If a car is driving down the street, going really fast, and it's got the wheels are in contact with the surface, so we've got rubber on concrete. Well, we know that rubber on concrete has a very specific mu value, a very specific value for the amount of friction, the coefficient of friction between rubber and concrete. But if you were to somehow, it gets windy out, and maybe you've got a reverse spoiler on the car or something like that, and you're going fast enough that there's an upward force, and the air gets underneath the car, and it lifts the car up a little bit, not off the ground, but just up underneath it, and gives sort of an upward force on the car. Well, the apparent weight of the car, because the weight of the car hasn't changed, but that upward lift of the wind on the car would actually make the car appear lighter because you're lifting up, so that it's actually the normal force, which is the scale reading, reduces a bit, so the car appears lighter and there's less contact with the surface. Well, once there's less contact with the surface, regardless of the mu, because the mu has not changed, the coefficient between those two surfaces hasn't changed, but because the upward force is there and the normal force is smaller, there's less contact with the surface and it becomes more slippery. Okay, so the normal force is the other thing, and the contrary to that is that, let's say you put a proper spoiler on a car, and when it's driving, the way that the spoiler is made, the air pushes on it. Newton's third law says that if the air is pushing on the spoiler is pushing down, and therefore the normal force increases, so the car appears heavier on the ground. It's not, the weight is still the same, the mg. However, there's another force pushing down, that spoiler force pushing down from the wind, and that would actually increase the normal force, which would increase the friction. Hence why we have spoilers on cars. It really increases the grip and the friction between the wheels, not because we've changed the mu, the two contact surfaces. We haven't changed the rubber and we haven't changed the concrete. However, what we've changed is the amount of force that's the normal force, which actually gives more grip and gives more friction. So this is the, oh, we've already written that. I'll write it again anyways because I started. The normal force. All right, so what we're going to do at this point is we're going to write here the equation for frictional force. So if we want to figure out the frictional force, it's mu F subscript n. Frictional force is the mu multiplied by the normal force. That's all you have to do. So in all these problems, if you're given the mu value, you just have to figure out the normal force from our free body diagram, and you're all set to go. I often call this, because it's the FUN, I often call this the fun equation. And of course, it turns out that mu has no units whatsoever. It's a coefficient, and by definition, a coefficient has no units. And this has units of newtons. So clearly, the force of friction has units of newtons. Right? That just makes sense. Okay, here's explaining friction. Here's a microscopic view of a frictional surface. So we have surface A, surface B. So the relationship between surface A and surface B would give us our coefficient. It would tell us how sticky the two surfaces are to one another. Let's say that surface A is sliding over top of surface B. Well, even though objects appear smooth on the surface, like if you rub your hands on a table, on a piece of steel, or on sandpaper, or on carpet, or whatever the case may be, when you actually look at most surfaces that appear smooth, they're not at all smooth whatsoever. Were you to get in there microscopically and look at them, what you would actually end up seeing is they're actually quite jagged. These are molecules, obviously, and the molecules are not evenly distributed on the surface. And if you went in further, you would just see molecules there and atoms. But at this point, we're not that far in. We're just microscopic, not nanoscopic or anything like that. So when you're looking at these, the surfaces are actually quite rough. And so even those surfaces, as we talked about before, never really contact each other. They never really touch each other. As they approach each other, you'll see that these little grooves and grips get stuck on each other. So if you're trying to slide this piece over top, this little edge here perhaps might hit this edge, and even though they don't touch, you're going to notice that Newton's third law says that if the repulsive force of this is pushing here, this is pushing back, and you're going to feel a net friction pushing back this way as you try and slide the object over. The more grippy two surfaces, it means that there's more microscopic bumps and grooves, and they're deeper and bigger. The smoother a surface gets, the smaller the profile of this would become. It'd look more smooth, there'd be bigger gaps in between it, and the profiles wouldn't be as deep. Whereas here, when you have quite a bit of friction, the profiles are quite deep. So they can kind of nestle into each other. Now what this does, this leads us to one more part that's really important. And that really important part is that there's two different types of coefficients. I've written mu here just singly. There's actually mu subscript s, which is static friction, and mu subscript k, which is kinetic friction. Now what this says is that if we were looking at this object, and let's say it's not in motion yet, these grooves could just settle nicely into each other and they'd be stuck there. When you first come up to push this object, well, it has inertia from mass, obviously, but there's also this backwards force that we have to worry about, which is from the friction. And in order to get it to, once it's settled into these grooves, to get it to move out, what you would actually have to do is push a little bit harder to get it first moving. But once it's moving and bumping around and jostling in and out of these grooves, it's actually a little bit easier. So it turns out that the value of friction for something that's stationary is slightly more than something that is already moving, or kinetic in that case. Okay, and we'll flip the sheet over and we'll take a look at that. So what you'll see here is that static friction is given this symbol, mu subscript s, and this is the friction at rest. Now, the reason why it only depends on the mu and not the normal force is that the normal force doesn't change whether you're moving the object horizontally or whatever, or you're moving it, or it's stationary. It doesn't change it. And mu subscript k is friction in motion. And these mu values are just numbers between 0, they go up to like 1, 2, 3, whatever the case may be. They have different values. And we'll look at that in a few minutes, at the different values that mu's can have. The following relationship exists, and that is that mu k is always less than mu s. Not by much, but a little bit. So the kinetic friction is always a little bit less than the static friction, right? So it's always easier there's always less friction when an object's already in motion than there is when it's stationary. We're often in our questions just going to leave out the k and the s and just talk about mu, the value of the coefficient of friction, but really there should be a distinction between whether it's moving, kinetic, or stationary, or static. One of these tables actually looks like this here. I'll click on this. Okay, and I just have to get to this link here, and you'll see here that static versus sliding. Sliding is kinetic. So for instance, if you want to look at a couple of materials, you might look at something like this: brass on cast iron. So if material 1 is brass and material 2 is cast iron, it has a sliding of 0.3. Now of course there is no static, and that's someone just hasn't calculated it yet or figured it out. Usually these are done via experiments. So you might look at, here's some here, let's see, rubber on dry concrete. So right here has a sliding friction between 0.6 and 0.85. So it's actually a variable depending on the type of rubber. In fact, you'll see that there's a whole entire industry called the tire industry, which has the values for rubber on all types of surfaces: dry asphalt, wet asphalt, icy asphalt, snowy asphalt. I mean, it goes on, and all the different types of tires and the amount of grip that they give is dependent on that. So in the winter we always switch to winter tires, and people wonder why. Well, the reason is that as rubber gets cold, it actually hardens, and the coefficient of friction drops. Sorry, the coefficient of friction, it goes way down, and it makes it more slippery. So what you do is in the winter you put on really soft tires, and so as the soft tires get colder, they harden up a little bit, but they actually remain and have a very solid mu value, or coefficient, on the asphalt or on the snow or the ice. And so a lot of physics and a lot of engineering and a lot of chemistry goes into this industry. It's a billion-dollar industry just on making tires and how to make these coefficients matter. So you'll be able to, you have access to this from the website, so you'll be able to look up all the different types of coefficients and their relationships and their values. Next, what we're going to do is we're actually going to look at a solution, and we're going to look at some problems and some examples of how to do them. So that's going to be our next little topic. After these examples, what we're going to do is there's a worksheet that we're going to do for 25 marks. And so the worksheet's quite extensive. It's nice and lots of different things there. There's a quick assessment, so a friction quick assessment that we're going to do. You'll be working on the problems that are related to that. There's a normal force and friction quiz, which is actually just going to be done as a practice quiz and assignment. We're going to work through that, and that's the whole package for friction. There'll be some review on that as well, but this is all we're going to be doing for the friction as far as that is concerned. Next, we'll look at looking at these examples in the next video.